I've been adding some short assignments. So 4.4 is the stuff that's dealing with the fundamental theorem, right? So we're kind of skipping through. You saw I put an optional assignment in there for 4.3. Don't have to do it. I would sort of recommend if you're going to be going into a field where you're going to want to be really prepared to have seen this before. I mean, I would recommend maybe looking at it, but that's kind of the last minute. Get everything else done first. So that one's optional. If you do it, I'll use it to replace a missing or low homework assignment. Not that that has that much impact. But that one you don't even have to do, right? So there's 4.2. I think there's one practice from 4.2, which is just a little bit of Sigma stuff. I think I had you add up a couple of areas using some rectangles, just like figure out what the widths and the heights are of the rectangles. Pretty quick one. And then 4.4 is where the action is. That's the stuff that's the really important stuff, right? Using the fundamental theorem, which we're going to practice today. The first one is just a conceptual one. The people that are done with that, I'm looking on there. It looks like it's taking about an average of about 10 minutes to do that one. Really, I saw you got one left on that, but that goes pretty fast, right? That one, where it's just kind of thinking about the concepts behind. How do we add up area? And we'll review that stuff today, but not really doing any problems. The second and third assignments are 7 problems apiece. I made it really short. It's just getting some practice. I kind of divided it up. So the first one is going to be polynomials and just kind of using the power rule for integration, which is what we'll practice today a little bit. And then, so that's the second assignment. The third one is doing a little bit of trig stuff. But once again, it's kind of it's really short. I'm just wanting these to be short, but I want them to be divided up so each one talks about something specific. Okay, so for today then, let's kind of review a little bit. Let's kind of get our bearings, and we'll look at some practice problems related to the assignment stuff. So we know we go back about a week. We were looking at anti-differentiation, which is kind of the opposite of differentiation, and we said that if we take the antiderivative of some function, that's equivalent to playing calculus Jeopardy. And what we get back from that is an antiderivative plus some constant of integration. So what we're getting back is a function. It's not a number. Yes. Eric, go ahead. Oh, I forgot about her. Yep, I'll send her. Sorry. Bye. SBAC testing. Yeah. 205. I think it is. Yeah. Let me pretty sure. You are, yep, 205. Yep. All right. Okay, so that's, we got used to that, right? We got used to taking antiderivatives, and then we launched into something seemingly much, much different, right? We were looking at trying to find areas under curves. And after wading through a lot of math, we proved the fundamental theorem of calculus, right? Which tells us that just unexpectedly, if we want to find the area under some function on the interval from x equals a to x equals b, it ends up being related to that antiderivative that we did. It ends up being, by the fundamental theorem, the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. Just really unexpectedly, it works out that way. So it just seems like completely different stuff. But we can use that same concept to add up areas under curves, okay? And so if we wanted to add up, for example, the area, I don't know why I have that there. Just gonna get rid of that. So there are some properties that we talked about that go with that. We define the area under a curve as being positive when it's above the x-axis, right? And it's positive when we add it up from left to right. If I reverse any of those things, it makes it negative, right? So if we have area below the x-axis, the area between the curve and the x-axis, when the curve is below the x-axis, that's added up as negative area. And if we add up area backwards, that also makes it negative. And we can see that in these properties that we looked at. So let's just kind of take a quick look at these. Just make sure they all make sense to you. So how about this first one? This makes sense. The integral, we call this, by the way, when we calculate area this way, we call it a definite integral. It's definite because we don't end up getting some infinite family of functions. We get back a definite answer in the form of a number. We wanted area under the curve expressed as a number. So does this make sense then? The definite integral of f of x from a to a is equal to 0. Why does it have to be 0 there?
Because the interval's length is 0, ergo there's no area.
Yeah, there's no width to this area, right? We're adding up the area under the function f of x from x equals a to x equals a, so there's no width to that interval, and so therefore the area is 0 by definition. Okay. How about this one? What's this second one saying here? Integral of f of x dx from b to a equals negative integral of f of x dx from a to b. What's that reminding us about? Backwards. Okay, so if I add the area backwards, if I reverse the direction in which I'm reckoning the area, then it makes the area negative, right? Okay. Now we also looked at a couple other little tricks, right? And these are great tricks. They don't always, like our book, they show up in, but some, like when I was auditioning calculus books, and this is one of the things I looked for. A lot of books, they don't even put this in the book. These are really useful tricks. If we have an even function, so think what an even function means. It's got symmetry about the y-axis. Remember that our test for even functions, we went through this yesterday, but not everybody was here, so let's just quickly remind. Even function test is f of negative x equals f of positive x. If that's true, if I plug in a negative x and I get back the very same function I had to begin with, then it's an even function. It's got symmetry about the y-axis, and if we're integrating over symmetric limits of integration, we know that we're going to get the same amount of area to the left of the y-axis that we get to the right of the y-axis. And we just looked at an example like x squared, I think, in class, but it could be any even function. So what we're able to do then is we're able to use the trick. We can say that this integral is equivalent to saying 2 times the integral from 0 to a. Let's just add the area from 0 to a, which is easier to do. 0 is a really easy limit to use when we're doing a definite integral, and just double our result. And even better than that, if it's an odd function, and remember that our odd function test is f of negative x is equal to negative f of x. Odd symmetry being rotational symmetry about the origin. If that's true, well then we know that the area to the left of the y-axis is going to be the opposite of the area to the right of the y-axis, and if we're integrating over these symmetric limits, we know we're going to get 0 every time. Okay? So let's use that knowledge to look at a couple examples here and see if we can come up with good answers to these. Oh yeah, that's good. So what about this first one? They're telling us in a problem like this. Now notice that there's no calculus to do. This is all purely conceptual, right? We don't know what f of x is. We don't know what g of x is. But we know that the area under f of x from 2 to 4 is 2. The area under f of x from 2 to 7 is 6. And the area under g of x from 2 to 7 is 2. Okay? So then, nobody say anything here, but think about this for a second. Oh, that's kind of a gimme. What's going to be the area under that curve? What do you think? You say, okay, Ron's telling me 0, right? And we know it's 0 because we're going from 4 to 4. It's got no width. So that area is 0. Okay? How about this one? The area under the curve g of x from 7 to 2, based on what we know about those functions, what's that going to be? Negative 2, right? Because we're adding up the area backwards. Okay? So it's going to be the opposite of this area. So it's negative 2. Okay? How about this one now? What's going on here? I've got the area under 2 times g of x from 2 to 7.
4.
Okay, it's going to be 4. Good. And how come?
Because when you just take the 2, it's constant. You move that up front.
Good, exactly. That's how we want to think about this, right? We can always, if we've got a constant inside our integrand, we can always pull that out in front of the integral. And so we could rewrite this one as 2 times the integral of g of x dx from 2 to 7. And we know that that area right there is equal to 2. So I just get 2 times 2 equals 4, right? And then how about this one? The area, oh, I know, there's one we forgot to put on there. I need to add it. Need to add it to the list. Okay, so what about this? If we've got the integral of f of x from a to c plus the integral of f of x dx from c to b, what do you suppose that's equal to? From where? A to
B.
B. Okay, think why. We're adding up the area between x equals a and x equals c, and then this is adding up the area between x equals c and x equals b. So those two areas, if we push them together, it's just one continuous interval from a to b, right? So do you see then that that's got to be our result, right?
Could we think of it as because the C's are on top of the bottom?
Well, I mean, you can maybe see that pattern, but you really just want to think of it as when we're adding up area like that. Let's look at an example with a graph. So what if we did this? And let me take a picture of this guy. I want you to conceptualize this. This is another thing that's pretty useful in calculus. We can take advantage of this. So there's our property. Now what happens? So let's make this, what if we make this A and this B and that C? So then the first part is just going to be this part right here. Well, I need a function too. There's my function. So if we look at that part, that's just going to be the area from A to C, right? So that's going to be all that area right in there, right? This part right here is going to be from starting at my lower limit of C, so I'm starting the area at C and ending at B. So it's this area right there. And then the total is just all the way from A to B, right? Okay. Yes, sir.
That also works if C and B
yes,
switch places, right?
Yeah, it does, exactly. So very good. So we could also,
That's what
yeah, we could do this. Okay, very good. So what if C is not in between A and B? I want to show you that it still works, right? Well, actually, you tell me why it still works. So now let's just arbitrarily say that's A, that's B, and that's C. Okay? So if I'm adding up the area from A to C, then so this represents all of this area right there, doesn't it? Right? Okay. What about the area from C to B? The area from C to B represents this area, but I'm going backwards, exactly. So it's negative area, isn't it? Right? So if we arbitrarily, what if we figured out that this whole thing, if this area right here, all the area that I've drawn, if that area has a value of 10, and the area from B to C, let's say that that has an area of 7, well then the area from C to B would be negative 7. So we're just reversing all that area and getting rid of it, we just end up with that much, right? So even if C isn't in the middle, it doesn't matter. We can just generally apply this really cool property. It doesn't make any difference what the relationship is between A, B, and C. That's always gonna be true every time. Yeah, I think it's called the summation of area property or something, I can't remember what it's called, but, let's apply it. So what about here then? We're gonna need it here. So how can I calculate the area between 4 and 7 from knowing those areas?
Subtract the
Okay, so I could do the area from
2 to 7.
4 to 2, and then from 2 to 7, right, for example. Okay, I could break this up into, down here, the area from 4 to 7 I could write as integral of f of x dx from 4 to 2 plus the area under f of x from 2 to 7, right? As long as the upper limit of my first area corresponds to the lower limit of my second area, it has to work, doesn't it? So what do those add up to? What's the area of f of x from 4 to 2?
4.
Negative 2, right? Okay, so that's going to become a negative 2. What about the area from 2 to 7? That's 6. Okay. So we get 4 for our answer, right? Okay? See how that works? We just have to find a way. This has to, when we add up these separate integrals, we just have to make sure that our starting, lower limit is 4, and that our final top limit is 7. Okay? And we have to have some common boundary in between the two. Okay? Okay, what would this be? If I want to find the area under the curve g of x minus f of x. Okay? So that seems a little strange. I'm finding an area, we could think about that as being an area between curves if we want to try to graph it. But all I've got to do is use my property of integrals that I can just integrate term by term, just like we differentiated term by term, right? We've talked about that. Because the two they're related to each other, it's not surprising that I can treat multiple terms in the same way, right? So then we just end up with this one. This just becomes the integral of g of x from 2 to 7 plus dx minus the integral of f of x dx from 2 to 7. And what do we get? 2 minus 6 is negative 4, right? And then, we get the idea. Then here I'd end up with 3 times the integral of g of x dx from 2 to 7 minus integral of f of x dx from 2 to 7. You get the idea. Okay. So what about something like this then? So we just got a bunch of these properties we can apply. So what about this? We want to evaluate this integral, this definite integral. But you don't lose sight of what it is, what it represents. It's area, right? And not a lot of times, but sometimes it's much, much easier, rather than having to do an integral, actually do calculus on a piecewise function. In this case, why do that? Because we know that this is completely equivalent to the area under the curve. If we can add up the area under the curve geometrically instead of having to do calculus on it, it's the same answer. So why not do it, right? If we look at this piecewise function, f of x equals 5 whenever x is less than 3. So here's 3 on the x-axis. Yeah, there's 3, right? So here's 3. So then this is the boundary line between the two behaviors. right? Everything less than 3, we just get the simple line f of x equals 5, and there it is. Right, there's 5 on the y-axis. So if we're adding up area from 0 to 5, between x equals 0 and x equals 3, that's the function that's determining the height, the top of the area, right? Well, that's pretty easy. What's the area of that piece? 15, yeah, 5 times 3. Okay. To the right of that, we get the line 2x minus 1. So there's the line. Y equals 2x minus 1, right? So we're going from 3 out to our upper limit of 5, so it's got a width of 2, and then that's just a trapezoid. What's the area of that piece?
Split it up to the square of the triangle.
Yeah, you could break it up that way if you want to, right? So we're going to get 2 by 5 is 10, right? And then this is, what's our upper limit here? It's going to be,
Yes.
so let's see, that's 9. Okay, so then that height's going to be 4 times 2, and that's 1/2 of that, right? So we end up with 4 and 10 and 15. That's pretty easy, right? We'll just add up the area that way rather than having to set this up with some complicated integral, right? Okay. So when you can, take advantage of that. I think we can skip this. Let's maybe look at just one of these. Well, let's look at this guy real quick. So once again, we're not doing any calculus here. They're giving us an area, and just by using properties of integrals, we should be able to come up with these answers without having to really do anything, right? So what if we want to answer this question right here? What if we want to find the area under this curve? Okay. So they're telling us that the area under that function from 0 to 2 is 32, right? Well, what have I done to get this integrand instead of that one?
Pull it like that.
Yeah, I just pulled, I multiplied that by 1/6, didn't I, right? So this is just equivalent to 1/6 times the integral of 6x times 4 minus x dx from 0 to 2. And we know that this whole thing, they're telling us that whole area is 32. So what do we get? 1/6 of 32, right?
So 16 over 3.
So 16/3 would be the area. Okay. Does that make sense? Okay, and then here, I would just be taking this area function and have to multiply by 2 to get 12, but I'm adding it up backwards. So we'd end up with negative 64. Okay. What about the bottom one? Does something look fishy about that? We can't do this without using calculus, right? This is one we can't do because we know that the area from 0 to 2 equals 32. Do we know anything about the area between 2 and 4? No, we don't, right? We can't just assume that it's double this because the function's not linear, right? So we don't know. That's one where there's not enough information. Unless we actually do the calculus, right? And let's practice that.
So if it asks us to use only that,
Yeah.
we would say not enough information, even though.
Yeah, so on your homework, there'll be 2 options. It'll show up as either there's a box you can fill in or you can check, that's option 1, it's like multiple choice, or option 2 is there's not enough information to do it without using calculus, without using the fundamental theorem. Okay. Okay, what about this? So this time, we're not using any tricks, we're just calculating an area. Okay? So we got to use the fundamental theorem of calculus, right? We've got to take an antiderivative and then evaluate that antiderivative, find the difference in the value between 14 and 10. Okay? So,
Go get decimals.
well, I mean, you can.
Because the terms are being multiplied, can't we split that up?
Okay, so there's, I'm glad you brought that up, because the answer is no, you can't. right? Just like we couldn't when we were when we were differentiating, if we had something like if we had the derivative of, say we had y equals x squared times sine x, for example, right? When we took the derivative of that, unfortunately, we were not able to just say that's the derivative of x squared times the derivative of sine x, right? We had to use the product rule, right? It was more complicated, right? So that is not equal to, y prime is not equal to 2x times cosine x. I have to use the product rule.
So
Okay.
we have to use a reverse product.
Well, so you're right. So we would have to use some kind of complicated reverse product rule, and we don't even know that's a kind of a higher technique in integration that we won't even get to this year. Okay, so that's off the table for us. Yeah.
No, we just apply.
Exactly. Right. What we would do instead, and this is really important when we're doing integral calculus. Our goal, a lot of what we do. And we'll get just kind of a glimpse of this. You know, we're not going to be able to get into really complicated stuff. We just don't have time. But a lot of what we do is we're going to take the integrand, which is what's inside the integral, right? That's the function that we're playing calculus Jeopardy with. A lot of what we do is we want to kind of, I call it pre-write the function. We want to write it in a way where we can do calculus on it, where we can do an antiderivative. We can't do an antiderivative on that because it's a product, right? But if I just multiply it out, and look what we get.
So we won't have to do any derivatives like x squared sine x.
No, at this point we won't. And there's some techniques that you'll do next year. You'll learn to integration by parts. We'll do U substitution. That's really the only technique that we'll learn this year. Then there's some other techniques you'd use for other types of hard integrands. Integration by parts, you can use the method of partial fractions, you can use trig substitutions. There's kind of a list of a few techniques you would use depending on what the look of the integrand was. And that's what you'll focus on more next year in calculus. You know, I mean, like when you get through the first class into the second class, okay? So what we would do here though, is we're just gonna multiply this out. So if I do multiply this out, what do I get? If I distribute, I'm gonna get a 10x, and I'm gonna get a positive 14x, so I'm going to get negative x squared plus 4x minus 140. Did I do that right?
No,
I didn't. Not surprising.
28x.
28x.
24x.
24x. 24x.
Yeah, off by 4. Not bad.
Closer than that. Okay? Now that's something we can deal with, right? Now I've got my integrand is a polynomial, and we can just integrate that term by term, right? You don't have to write this out. I'm going to write it out one time, but after this I never will because it just takes too much time. What we're essentially doing now is we're going to break this up into 3 separate integrals. We're going to get the integral of negative, and I pull the negative out front, negative x squared from 10 to 14 plus 24 times the integral of x from 10 to 14 minus integral of 140, and I can either pull the 140 out front or I can leave it inside, doesn't really matter in any of these cases. And so we get the answers. Well, what is that? What's the antiderivative of x squared?
X cubed over 3.
X cubed over 3. Okay, so I'm going to get a minus x cubed over 3. But because I'm doing a definite integral, I'm not going to say negative x cubed over 3 plus c, right? We're looking for an area instead. So we don't mess around with the c when we're using the fundamental theorem. So we're going to evaluate this from 10 to 14, and that's going to give us a number, okay? Plus, what about this guy? I'm going to get 24. What's the antiderivative of x? What's the antiderivative of x? Look, what's the antiderivative of x? X squared over 2, right, good. X squared over 2, and we're going to find what the area is of that piece of the curve from 10 to 14, And then finally, we get minus, what's the antiderivative of 140? 140x. Okay? From 10 to 14. So what's that mean? Okay, that means that this whole part right here is going to be minus, what does this mean? This is that weird notation. It means I'm going to evaluate this at 14 and then subtract its value at 10. I find the difference in the values at the upper limit and the lower limit, right? So I'm going to get 14 cubed over 3 minus 10 cubed over 3. Whatever that is, that's just going to give me a number, right? Plus, how about this part? I'm going to get 24 times the value of this at 14 minus the value of that at 10. So I get 14 squared over 2 minus 10 squared over 2, right? Minus 140 times 14 minus 140 times 10. Yep.
Do you have to keep them all separate like that, or could you have it?
No, you could. You could lump them all together too. If you wanted to, we could, this is the same thing as saying, if I want to, I could just do negative x cubed over 3 plus 24, and 24x squared over 2, I could, really I could even just make that a 12, right? X squared minus 140x, and what Kirk is saying is we could do that whole thing from 10 to 14 also. Okay? It's fine either way. I think it's better in a way, well, very slightly better to do it this way, because sometimes what's going to happen is we're going to get pieces where, like, what if these were symmetric limits and this was an even function? We're gonna be able to sometimes make some of these go to 0. You see what I'm getting at? In some rare cases, it makes it a little bit easier to break it up into separate, smaller integrals that we're evaluating separately. But you can do it either way. So I can take this whole thing, and I can take this expression evaluated at 14 minus that expression evaluated at 10. Take your pick. Either way is going to work. Okay? Either way we do it, what do we get for an answer? Somebody jump on their calculator and tell me what we get here. So we're going to get, what about this part right here? Well, I've got a common denominator of 3. So I get minus 1/3. What's 14 cubed is what? Somebody? Elton, you got a calculator handy?
3,744.
3,700.
2,000.
2,744.
It's over. Yeah.
Minus 1,000, right? So that's going to give us 1,744 over 3. Yeah, so I get negative 1,744 over 3 from that first term, plus, here we said we could, I've got a common denominator of 2, so if I just pull that out front, I've got 12 times 14 squared minus 10 squared. So was that 196, no, 196 minus 100, so I guess get 12 times 96. I kind of screwed it up. I'm going to have to move down another line. You get the idea. So if I turn these all into numbers, I get negative negative 1744/3 plus whatever 12 times 96 is.
1,100.
What is it again? 1,152, okay. Plus whatever I get from this. So I could even pull the 140 out in front of that if I want to. I get minus, because that's a common factor, I can factor that out, times 14 minus 10, which is just 4. 4 times 140 would be 560. So I end up with a minus 560. So if I add all that stuff up down there, what am I going to get? Just some big number. What is it, somebody? Negative 1744/3 plus 1152 minus 560, and the grand total is
32 thirds.
what is it again?
32 thirds.
32 thirds. So that's the area under that function. If we, what did we just find? We found the area under this quadratic polynomial from 10 to 14. Works out to be 32 thirds. Okay?
Now, do you expect us to write all of that out? While you're just-
No, I don't at all. I don't at all. You wouldn't have to work. To me, the only steps you'd have to show for work would just be, you're going to find out what the antiderivative is. So if we're going to do this like Kirk, it would jump right from, it would go from here down to there, down to there, right? I mean, that's just some arithmetic, all you're doing there, right? Okay? Okay, what about this one? That looks a little weird. That's not a polynomial. Okay, but there are two terms there, so I can break this up into two parts, right? First part's easy. Antiderivative of 3x is just, what, 3x squared over 2, right? That part's no big deal. But what do I do with that square root?
To the 1/2.
Okay, I want to write it as power, right? Because what are we really doing here? We're using that antiderivative, everything we've done so far, we're using that antiderivative standard form. We know that the integral of, what do we say, u to the n du is just what? What's the antiderivative of u to the n?
U to the n plus 1 over n plus 1.
And then, if we're not doing a definite integral, we add a plus c, right? But we don't care about that for what we're doing. We're just using the integrand part of that, right? Or the antiderivative part of that, okay? So we'd have to rewrite this thing as integral of 3x plus x to the 1/2 dx, and what do we get? Well, you already told me that the antiderivative of x is x squared over 2, so I'm going to get 3/2 x squared, right? What's the antiderivative of x to the 1/2?
2 thirds x to the 3/2.
Okay, does that make sense? X to the 3/2 over 3/2, which means times 2 thirds. And then we're just going to evaluate that from 0 to 4. Now, in this case,
That should be
the
3/2.
Kirk's method is
That should
way
be
better.
3/2 x.
What's that?
Can that be 3/2 x to the 3/2?
Uh,
Oh, no, I see what you did. My
Yeah,
bad.
okay. So in this, for one like this, I'd say Kirk's method is the way to go, because when I plug 0 into this, what am I going to get? 0, right? So my answer is just going to be, if I evaluate this thing at 4, I'm just going to get 3/2 times 4 squared plus 2 thirds times 4 to the 3/2 minus, if I evaluate this thing at 0, 0, right? And so my answer is just that, whatever that is. What's that give us? 16, so I get 8 times 3, so I get 24 from the first term. 4 to the 3 halves is 8,
Yeah.
so plus 16 thirds. So that's my answer, right? Okay. Okay, what about this one? I got 2 terms once again, so I can break it up into pieces, right? So what's the antiderivative of sine, integral of sine x dx? Play calculus Jeopardy. The
Negative
derivative of
cosine.
what is sine?
Negative cosine.
Negative cosine. Right. So this one gives me a negative cosine x back. The derivative of what is cosine x? Sine x. And we're just going to evaluate that from negative 5/4 up to positive 7/4 pi, right? And so if we, let's break this one up into pieces. So that's going to give us, I can take the negative out front, I get cosine x from negative 5/4 7/4 pi plus sine x from negative 5/4 7/4 pi. Or I can do it all at once, doesn't matter, right? So if we look unit circle, it's not a color cookie, so that'll be yellow. This will be green. So negative 5/4 is where on the unit circle? Okay, so like right there. 7/4 pi. No,
Will it be the same?
you have to self-convert on that. It'd be the same spot, wouldn't it? Because I'm going to go pi and then another 3/4 pi, so they're in exactly the same spots. Oops. Okay? And so, what's going to happen then? So I'm going to get, negative, cosine of 7/4 pi is what? And what are the coordinates of that spot? Think in terms of quadrant 1. What are the coordinates of that middle point in quadrant 1? Well, you could do the hand trick, right? It's going to be square root of 2/2, square root of 2/2. So these must be positive square root of 2/2, negative square root of 2/2, right? So the cosine would be positive square root of 2/2. Okay, so. But this is kind of silly that I'm even doing this, isn't it? Because what's going to happen?
It's all gonna go to 0.
It's going to go to 0, isn't it? Because the cosine of negative 5/4 is exactly the same spot. That's 0, isn't it? Plus, what about the sine? Well, once again, it's kind of silly. At 7/4 pi, I'm going to get a minus square root of 2/2 minus negative square root of 2/2. It all goes to 0. How come it all, does it make sense that it all goes to 0? It kind of does if you look at the picture. Can you tell me now why this goes to 0?
Has symmetry about the origin.
No, not about the origin. The symmetry is kind of hard to describe, but wouldn't you agree by looking at this, at least visually we can see it's consistent with what we got because the positive area and the negative area are just equal and opposite lobes, right? So it has to add to 0, doesn't it? And it did. Okay. Okay, what about this one? We can do this one really quick. Really quick. It's not 0.
Oh, no.
It's not 0, but we can break this up into pieces, can't we? Right? We could break this up into integral of sine x dx from negative 7/2 pi to 7/2 pi minus integral of 2 dx from negative 7/2 pi to 7/2 pi. Yes, sir.
You do that, so the same can go like to 2. Since it's negative a to a.
Okay, they're symmetric limits. Now the question is, are the integrands even or odd functions? Right? So in other words, we got to do the test. Here's, and this is kind of something, and we'll finish this one up tomorrow. This is a good, saves you can do this much more easily. You don't have to really do any calculus on this one if you think about it the way you were.